Hello Year 12. I'm going to apologise for three things. Firstly, I'm sorry this is a little bit late. Secondly, I'm sorry that I'm probably going to cough during this. And thirdly, I'm sorry because chemistry teachers as a whole have lied to you in the past. And you're about to find this out. A final apology, one that I forgot that I was going to make. This is probably going to be quite difficult for you to follow. Don't worry, we're going to spend a few lessons on this. It will make sense eventually. So, covering quite a few specification points in this video. And that's because we're learning about an entirely new concept to you that's going to be quite alien. So up till now we've been talking about electrons as living in shells, and that seems to make sense so far when we've been looking at the periodic table. We've always assumed that you have 2 electrons in the first shell and then 8 in all of the ones after that, and that all of the electrons in each shell are interchangeable. They're all basically the same. So hydrogen has 1 electron in the first shell, chlorine 2 in the first shell, 8 in the second shell, and 7 in the third. Try that for bromine. You put 2 in the first shell, you put 8 in the next shell, you put 8 in the next shell, and then you end up with a lot more than 8 electrons trying to go into the fourth shell. In fact, you're trying to get 17 in there. It doesn't seem to make any sense. It's in the 4th row of the periodic table, so you'd expect it to have 4 shells full, but you can't fit them all in. So what's happening? Well, firstly, I'm really sorry, but you've been lied to. The idea of shells of electrons at equal distance away is not really that true. It's better to think of electrons as being in energy levels that have electrons of roughly the same energy. So you can think of there being a first energy level corresponding to the first shell, second energy level corresponding to the second shell, third energy level corresponding to the third shell, and then a fourth energy level, and so on. And these energy levels split into subshells, and this is where we end up with more than 8 electrons in a shell. Incidentally, having more than 8 electrons in a shell is called breaking the octet rule. So this is what it looks like when they split up. I want you to ignore everything above 3D. You will not be asked anything above 3D. 3D is your highest orbital that you will think about, highest subshell that you will think about. So we have shells here, or energy levels, which I'd rather you thinking of them as. And then we have subshells, these bits over here, with the little letters by them. So, first energy level, you'll notice, has not been divided into any subshells. It's just got a 1s subshell, that is it, it's one subshell, it is one shell. That's because it's only for 2 electrons. Second one, which we know the second energy level definitely fits 8 electrons, has been split into a 2p subshell and a 2s subshell. The subshells are given these little letters after them, so you know what they're talking about. So 2p subshell means the p sort of subshell at the second energy level. You'll notice there's also a 3p subshell and a 4p subshell. So this is how we distinguish between the two, and they're going to be similar shapes. Third energy level has been divided into 3 subshells. Now we're going up in energy here, and you'll notice that the 3d subshell is higher in energy than the 4s subshell. This is where some of the complications have happened, and it's important that we remember this. 4s subshell is really low in energy, 3d is really high in energy. I'm going to be discussing this in the lesson as to why that actually is, but you just need to make sure that you know that 4s is lower than 3d. So, the order of the subshells is really important. Subshells tell us where electrons are going. Okay, so you know how atoms want to be in the lowest possible energy. They like being low in energy. That means that they are stable. So if we put electrons in from the bottom upwards, it is harder to remove them. A high energy electron is very easily to ionize. A low energy is very hard to ionize. It's sometimes quite easy to think of this energy as the distance from the nucleus, but that's not actually, strictly speaking, true. This is more about the energy, because this 4s subshell is further away from the nucleus than the 3d, but it is lower in energy. So we need to think about how we represent this. So this is energy, it's lower in energy. It's lower in energy, it's more stable. So we put electrons in the 1s subshell first, then the 2s subshell, 2p subshell, 3s, 3p. then 4s, then 3d. Now, if you look at your periodic tables, you'll see that you have elements divided into sort of some textures, and there's a bit of a cutout where you go to the transition metals. That transition metal section is called the D block because those are where D electrons are being filled. I'm going to talk more about how this notation gives us the periodic table in the lessons. So there's one more subdivision, okay, and that's the orbital. An orbital is a region of space which can contain 2 electrons. Electrons we don't want to think of anymore as these solid balls that are floating around on a ring. Think of them more as a fly. They're kind of dotting around the room, but they're following a roughly fixed path. They're in roughly the same place every time we see them. If we look at them enough, we can average them out as an area that they will be found in. So orbitals are a region that contains that can contain 2 electrons, up to 2 electrons. The electrons are put into orbitals. So this is kind of our new version of the old circle around the nucleus idea. We've now got these things called orbitals, which is the space the electrons are occupying. So s subshells have 1 orbital in them. That means they can only fit 2, and they can only fit 2 electrons. 1 orbital fits 2 electrons, remember. So that's why at the top of the periodic table, in the first period, you only have 2 elements because you have 2 different. You have helium and hydrogen filling up the 1s subshell, and there's only 2 electrons you can fit in there. In the second period, you've got the p subshell as well, which adds another 6 electrons we can fit in. So that's how we can get up to 8 electrons in the second period. We can put 2 in the first, put 2 in the 2s subshell, and then 6 in the 2p subshell. So p subshells, 3 orbitals, s subshells, 1 orbital. D subshells have 5 orbitals in them, so it can fit 10 electrons. So if we look down to the fourth period, where we had all that trouble with bromine, where we were trying to fit 17 electrons in, we're filling up the 3d orbital, but it's an extra 10 electrons we can find space for. Now, you're probably not wondering this, or scared of thinking about it. What one of these orbitals look like? Unfortunately, they're not so simple as the rings around the nucleus. Well, the s orbital is, we've got a round s orbital, spherical. So all the s orbitals will be spherical, just slightly bigger each time. The p orbitals are kind of like flower petals, okay? You have one with the petals going along the z-axis, one along the y-axis, one along the x-axis. So there's 3 of them, and you can fit them all in around each other. Now there's 5 different d orbital types. We have this one, which is a little bit weird, it's a little bit like a dumbbell. This one, and these ones are all sort of different reflections and translations of the same one. You should know what the p orbitals look like and what the s orbital looks like. D orbital, less important, but you should know there are 5 of them. Finally, for this week, let's think about how this gives into the electron configuration as we were trying to do at the start. So, rather than thinking about what shell things are in, we want to think about what orbital electrons are in. When we put electrons into orbitals, we put them so that we can fit the most. Electrons like to be on their own more than they like to be paired up because of repulsive forces. However, they want to be in the lowest energy possible. So what's going to happen is we're going to put 2 electrons, or the first 2 electrons, into the 1s subshell, second 2 into the 2s subshell. So now we're at the structure of beryllium. After that, we're going to put 1 electron into the 2p. The next electron is going to go in here, and the third electron is going to go in here. So once we've got to this structure, we've got one on its own in each of the p orbitals. We then go back and start pairing them up, because the electrons are kind of like people on buses, they're reluctant to pair up with each other. Once we filled up the 2p subshell, we then go up to 3s, put 2 in there, 3p, put 3 in individually, then go back and put another 3 in on top. Then the 4s is the next lowest in energy, so we put 2 in here. Then we go to the 3d subshell. Now, we're going to spend a lot of time going over this in class, so don't worry too much if your head's a bit of a mess about this at the moment. Just make sure you go through your notes carefully, write some Q questions, pause, rewind the video if you need to go back over things. Take all the time you need on this. I will expect you to have your notes written with summaries on Wednesday, where we can properly have the discussion on this. Thanks for watching.